Welcome to Calculus.
We've always been good at math. How hard could calculus be?
On this episode, Stevenson will demonstrate
So you may be wondering, what are we going to use the second derivative for? Well, welcome in concavity. Basically, concavity is how the graph is looking, right? How is it? We can say it's concave up or concave down. So let's talk about this. So here's a picture of x cubed. Okay, we can see it rises the whole time. It's increasing the whole time, but there's portions of it that turn in different ways. So concavity can be thought of as how is the graph turning. So if you look at the tangents, so at 0 at the origin here, that would be what we call a change, potentially, or a point of inflection. Notice something's happening. The whole graph is increasing, but do you notice the tangent lines as you're getting closer to 0? Do you see how they're becoming less positive? So we're saying the derivative is decreasing. So notice when the derivative is decreasing, that portion is what we say is concave down. And if you look past the origin here, do you notice if you pick different values for the tangent lines, do you see how they're becoming more positive or a steeper line there? So they'll notice the derivative of the tangent lines, those slopes, is increasing. So we say it's concave up here. So this idea of concavity relates to the first derivative, but in terms of how the first derivative itself is behaving. So here's a definition of concavity. So we say a graph is a concave up on an interval if its y prime is increasing. Well, wait a minute. If the y prime or the derivative is increasing, that's talking about the rate of change of the derivative, right? So we can think about that as the second derivative. And it's concave down. A graph is concave down on an interval when its y prime is decreasing. But again, if you talk about when the y prime is decreasing, now you're talking about how its derivative is changing. So we can think of that as the second derivative being negative. So there is something called the concavity test, and it essentially just says what we just came up with. A graph is concave up on any interval when the second derivative is positive. And a graph is concave down on any interval when the the second derivative is negative. So here's two pictures here. In the book, it also has this side note, and it talks about how if you draw a secant line, you can also visually see the concavity. Okay, so if I draw a secant line here, notice my secant line point is above this part of the graph here. And then notice this secant line is below this part of the graph here. So how do we know when a graph changes concavity? Well, that change of concavity is called a point of inflection. Now this is really important because this process is very similar to finding critical points, but they do have a slight difference. So a point on a curve where the second derivative is positive on either side or on one side and it's negative on the other is a point of inflection. So what that means is there must be a change in sign. That's super, super important. So where do you look? Remember when we're trying to find extrema, we look at our critical points and we look at when the first derivative is 0, it doesn't exist. The same idea applies with points of inflection, so that's handy. So you look at where the second derivative is either 0 or undefined. But remember, don't assume it's automatically a point of inflection. You must have a change in sign. If there's no change in sign, it is not a point of inflection. But Stevenson, how does it change sign? It doesn't matter. What matters is that there's a change in sign of the second derivative. That means that point you're looking at is in fact a point of inflection. So remember, where do point of inflections exist? Where are the candidates? When the second derivative is either 0 or undefined. Now, the second derivative is also handy for finding local extrema. So what this says is, suppose you have a point where your derivative is 0 at that value. So that would be a critical point, right? And at that point, the second derivative is negative. Well, wait a minute. If the second derivative is negative, we just learned that it's concave down. Then doesn't it make sense that f will have a local maximum there? And the converse of that, or the reverse of that, is true. If the derivative at some point is 0, okay, that's a critical point, but the second derivative is positive, that means it's concave up, so that it makes sense that f would have a local minimum. So sometimes it's easier to use the second derivative to test for local extrema instead of the first derivative. So what this tells you is that so the test requires us, first of all, to know that f double prime only at C itself, it is not in the interval. So you're only looking at one particular number. So be careful with that. You have to understand that element. So this test is really easy to apply, but here's the bad news. The test fails if your second derivative is 0 at that point, or if the second derivative fails to exist altogether at that point. So what that means is it's a little temperamental. So if you try to do the second derivative test and you come across those items in red, you may want to resort to the first derivative test instead. So like it says in blue, the second derivative is just much harder to find than the first derivative. But when this happens, we go back to the first derivative test for local extremes. So again, you have two tools. You'll most likely use the first derivative test. However, sometimes it's handy to know the second derivative test.